Our next lesson is called Tilted Squares and Square Roots of Non-Perfect Squares. So for the opening exercise, I'd like you to try the problem on your own. It says, given the area of a triangle is A equals 1/2 base times height, find the area of triangle A. So you can see to the right, there is a picture of triangle A. B is for base, H is for height. I want you to pause the video and try the opening exercise and then resume the video to go over the answers. All right, now that you had an opportunity to try that on your own, if we look at the formula A equals 1/2 base times height, we have a base of 4, as you can see drawn on the picture, and a height of 5. So 4 goes in for B and 5 goes in for H. And then when you do the math, you have half of 4 times 5 being really half of 20, which is 10 units squared. Now we'll move on to example 1. So our objective in this question is, what is the area of this square? Now, when I look at this square compared to the lesson we had previously, this square is tilted. So in order to find the area of a square, I'm supposed to take the side and square it, which means take the side length and times it by itself. The problem with a tilted square is you cannot count the sides. It's not like in the previous lesson where we could measure the distance between the 2 points because of these diagonal lines. So what we want to do is create a square around the tilted square that will allow us to work with shapes that we can find the area of. So I'm going to draw lines around this tilted square. Notice that the lines I'm drawing are touching the 4 corners. And that just created, first of all, a larger square. One that is right side up, right? It's not tilted. It's totally vertical or horizontal lines that I can count the length of. And if you look inside that, we've actually created 4 little triangles. So we've got triangle 1, triangle 2, triangle 3, and triangle 4. So we'll refer to those triangles with those numbers, and we'll refer to this larger square as square B. And the purple original tilted square we'll call square A. So square A is too hard to find the area of. What we could find the area of quickly is square B. And if we take a look at what's inside square B, isn't that really just the area of square A plus those 4 triangles? So the area of B you will get by finding the area of A plus those 4 triangles. And the reason I can say the 4 triangles is because if you take a look, all these triangles are the same size. They have side lengths of 2 and 3, 2 and 3, 2 and 3. So all those triangles are the same. But what that tells me is if I can work backwards now and I can get the area of A by doing the area of B minus those 4 area of the triangles. So I'll show you what I mean. Let's find the area of square B first because I'm able to count that. So 1, 2, 3, 4, 5. The side length is 5. So if I'm finding the area of square B, that's A equals S squared. My side is 5. So that means my area is 25 units squared. So now I know the area of the larger square. Now I'm going to find the area of one of these triangles. So we have A equals 1/2 base times height. We know that from up above. We are going to find the area of triangle 1. So we would do A equals 1/2 base times height, which is equal to 1/2. Okay, doesn't matter which one we use. So I'm using triangle 1, and I can either make the base a 3 or the base a 2. So I'm going to have the base be 2, and that means the height is 3 when I count that. So base of 2, height of 3, and that's equal to half of 6, right? Which is 3 units squared. Now, again, if I go and look at all these other triangles, they all have 2 and 3, 2 and 3, 2 and 3. So it does not make sense to keep using this formula 3 more times. All we have to do is realize that one triangle is 3 units, then all 4 triangles would be 4 times 3, which is 12 units squared. So that means I can finish by finding the area of A by taking square B and subtracting those 4 triangles away from it. So that's going to be 25 minus the 12 for 13 units squared. So, similar to us using the squares where we could count the sides to show you perfect squares, we're showing you here that there are numbers that are non-perfect squares. Showing you the tilted square and that we can't count those sides shows you that when we go backwards from a number like this, a number that's not a perfect square, we're not going to get a nice number. So let's keep moving forward together and dig a little deeper here. Number 2 says, which 2 perfect squares is the non-perfect square closest to? So let's start thinking of some of our perfect squares. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. So there's the list of our first 5 perfect squares. And we got 13. So 13 is going to fall in here, right? So it's going to be between 16, I'll do 9, and 16. Now, the next one says, determine which, this is important, counting number the square root of the non-perfect square is closest to. So if we know the square root of 13 is somewhere between 9 and 16, without using a calculator, is 13 closer to 9 or is it closer to 16? So 13 is 4 away from 9 and it's only 3 away from 16. So the one it's closest to would be 16. So we are going to take the square root of 16 and we would get 4. So 4 is the counting number that if we took the square root of that non-perfect square 13, it would be closest to. So next, we should be able to place these numbers on the number line just like we do with perfect squares. So we're going to place the square root of the non-perfect square on the number line below. Now, reminding you, we're talking about the square root of 13 here. That's what we would have from our activity. So if we make a regular old number line, 1, 2, 3, 4, 5, 6, and 7. Another way you could think of 3 is as square root 9. And another way you could think of 4 is at square root 16. So we know it's going to be between there. And we said it was just slightly closer to 4. So I'll find halfway, and I'll go just a little to the right of that, and that's going to be our square root 13. Now, thinking back to what we talked about when we talked about the real number system, what happens when you take the square roots of this area on your calculator? So on your calculator, you're going to type in square root of 13. And when that happens, you're going to get approximately 3.605551275. And your calculator's only so big, so you don't see, and you kind of can tell from what you're seeing, there's no pattern, so no repeating pattern, and this number is going to keep going on forever. And is your result a counting number? No. Again, it's this long, ugly decimal that's not going to end, which means it's non-terminating, and it's not repeating in any way. So that makes this number irrational. And the reason is because it is non-terminating and non-repeating. You can also think of this as being what we're going to talk about on the next page. So we can refer to non-perfect squares in the following ways. A number whose square root is not a counting number. So when we were working with perfect squares, when we took the square root, we got a nice counting number. Like the square root of 25 is 5. The square root of 49 is 7. When we take the square root of a non-perfect square, we're going to get a number that's not a counting number. Reminder, the side length of any square is always equal to the square root of its area. And non-perfect squares, because of this, not getting a counting number and getting this long decimal that doesn't end and doesn't repeat, you're always going to result in an irrational number. So using that information, I want you to pause this video and try the practice activity. Determine the positive square root of the number given. If the number is not a perfect square, determine the counting number to which the square root would be closest. And you're going to circle the subsets of the real number system that the square roots of A through D belong to. So we're going to do this without necessarily using a calculator the whole time. You need to follow the directions that are inside the box. So you can see in part A, you're going to do 64 with a calculator. Part B, you're going to do 48 with a calculator. But then in C and D, 5 and 144, you're going to do them without a calculator. And then you're also going to circle the subsets of the real number system that these belong to. So at this time, please pause the video, then resume the video to go over the answers with me. All right, now you had a chance to try on your own. Let's go over the answers. So in part A, you were able to use your calculator. If I type in square root of 64 on my calculator, I get 8. So that is a counting or natural number, whole number, integer, and rational. In part B, with a calculator, I type in the square root of 48. I get a non-terminating, non-repeating decimal. So that tells me this is an irrational number, and I can tell if this number is not a perfect square, which this isn't, I'm supposed to determine the counting number to which this is closest to, and I can see from looking at my result on the calculator that that would be 7. Now, without a calculator in C, I know 5 is not a perfect square because there's no number times itself that will give you 5. So I know 5 is between perfect squares 4 and 9. So if I were to take and look at those, 5 is definitely closer to 4. So if I take the square root of 4, I get 2. So that means the square root of 5 must be close to 2, and it is definitely irrational. And then in part D, 144, I recognize as a perfect square because I can take 12 and multiply it by itself to get 144, which means this is a counting or natural number, a whole number, integer, and rational. And that concludes your lesson on tilted squares and square roots of non-perfect squares.